Hello guys, we'll be starting around 6:05. So please wait for 2 seconds. Presentation. Good morning, good evening, everyone. We are gonna have a session on development of open source hardware and IoT. Today we'll have two speakers. One is Devojyoti Pramanik, who is a senior of yours, and the other is our alumnus, Abhijit Das, who is working. So we'll have people from the industry as well as from the academics that will be speaking. Starting off, we'll be having Devojyoti, which will be followed by Abhijit. After that, we'll have a session on doubts and anything that you want to ask them, ask our distinguished speakers, and we'll be over with the session. So that's how the session will go. Right now, I'll may pass the mic to Abhinav, who will pass the mic to Devojyoti, and Devojyoti will start his event.
Yes, Abhinav, I'm ready. So let me know if my screen is visible. I'm presenting right now. Just a minute. Acha, there is echo from somebody's mic. Yeah. Is my slide visible? So just a minute. Yeah. So hi everyone. Myself Devojyoti Pramanik, a student of Electrical Engineering Department, currently studying in 4th year in NSCC. So speaking of myself, I have qualified for SIH 2020 semifinals, and I was also the among the top 10 teams in KPIT Sparkle. Apart from this, I have done many projects based on IoT and participated and secured positions in various hackathons. So I would like to talk on the topic of open source hardware. So what is an open source hardware? You can see the definition from the slide. The hardware whose design has been released to the public in such a way that anyone can make, modify, or distribute and use these things are known as open source hardware. So there are numerous number of open source hardwares ranging from computers to electronics to mechatronics and many others. Computers include EOMA86 compatible computer card, which contains a dual-core processor with 2 GB RAM and 8 GB of NAND, flashed pre-installed with Linux operating system. And we can also tell Raspberry Pi as an open source computer. Actually, Raspberry Pi is an open hardware with the exception of the primary chip on the Raspberry Pi, the Broadcom SoC, which runs many of the main components of the board, including CPU, graphics, memory, the USB controller, etc. So speaking of open source electronics, the one and only thing that comes into everybody's mind is Arduino. So I think here almost everybody knows what an Arduino is. For those who don't know what Arduino is, it is an open source hardware and software company project and user community that designs, manufactures single board microcontrollers and microcontroller kits for building digital devices. The hardware and software products are licensed by the following companies, as you can see in the slide. And I won't go much into details about these licensing. So basically, it manufactures a development board with the help of which we can do interactive projects, build prototypes, and basically have a whole load of development using these modules. So what is a microcontroller? A microcontroller is a compact integrated circuit designed to govern a specific operation in an embedded system. A typical microcontroller consists of input-output peripherals on a single chip, memory, and a processor. So here you can see in Arduino there is the Atmega 328P chip, which acts as a brain of the microcontroller. There are 14 digital input-output pins and 6 analog input-output pins. This Atmega 328P chip can be programmed using the USB, the serial connection using this USB port, and Arduino can be powered by a 5-volt DC connection present here. So this was a brief introduction of what an Arduino board is. The real work is development using it. What are the possibilities or what are the things that we can do with the help of this tiny board? So I asked from the chat that give me any example of real life problems that can be solved by using this board. Those who know what an Arduino is. Anything? Yeah, smart lights may be a thing. Okay, let's not. Yeah, smoke detector, that too. Okay, let's not waste any time. Let us move to the next problem, real life problem that we are currently facing. So wastage of household energy. So for example, if you work in an office and you leave your house by 9 a.m. and return from your work almost at 7 p.m., but sometimes you forget to turn off the lights or fans or whatever the appliance may be. So the appliance runs for almost 8 hours uselessly. The energy gets wasted. So to prevent it, what will you do? So anything from chat, what will you do? Anything that you will do to prevent the wastage of energy? Okay, no response in chat. No problem. So as we know that microcontrollers take input from input ports, processes the information. I think, yeah, we can do that. We can schedule appliances. That part I will come into the later part of this presentation. We can surely do that. So as we know, microcontrollers take input from input ports, processes the information according to the commands written in an integrated Atmega chip, and again sends the output through the output ports. So we have to use such a sensor which detects the presence or the absence of human body in a room. So the example of such type of sensor is a PIR sensor, which stands for passive infrared sensor. So most of the all of the human beings radiate a small amount of infrared energy, which the PIR sensor can detect. So what we will do is connect the PIR sensor to the microcontroller, and the microcontroller will be connected through a single channel relay, and in turn this relay will be connected to a LED bulb, which is connected to an AC source. So what will the PIR sensor do? The PIR sensor will sense whether any person is present in the room or not. So if the PIR sensor detects an infrared radiation, it senses that a person is in the room. It sends the signal to the microcontroller that yes, there is a person present in the room, and then this microcontroller processes the information and tells the relay to close its contacts. When the contacts gets closed, the circuit of the AC source gets completed, and the LED bulb switches on. Secondly, when suppose there is no one in the room and the PIR sensor does not detect any human being or any infrared radiation that is coming, it tells the microcontroller that no, I'm not detecting any signal. It sends 0 to the microcontroller, and the microcontroller in turn tells the relay to open its contacts, and hence the LED bulb turns off. To be precise, most of you are not familiar of what a relay is. A relay is basically a electromechanical device. So this is actually the circuit diagram of relay. So it contains 2 low voltage contacts and 2 high voltage contacts. 2 contacts where high voltage appliances are connected, and 2 low voltage signal contacts. So the low voltage signal goes from the low voltage contacts, and when the switch turns on, what it does, it powers the electromagnetic core present here. The electromagnetic core gets powered, and what happens? This strip present here comes down because the strip is attracted by the electromagnet, and hence the circuit gets completed and the appliance lights up. When there is no power from the no power from the power source, the switch gets turned off, the electromagnet demagnetizes, and what happens? These 2 contacts get open and creates an open circuit. Hence, the light source or the appliance that is present switches off. So this is the basic functioning of the relay. So basically putting these things all together, the Pir sensor commands the microcontroller whether the person is present in the room or not. This in turn communicates with the relay, and the relay switches on or switches off to turn the LED bulb on or off. So, just a minute. Somdev, can you please open the chat box and check the messages? Hello, Somdev, I'm audible.
Yeah, please go on.
Yeah. So, yeah, I got it. Hello, I'm audible. Hello. Yeah. So, yeah, so there's a question from Ashwarya, buddy. Just let me open the chat. So, with the help of microcontroller, we can interface various sensors and control. I mean, we can take inputs from them, and we can send outputs to the various actuators. Suppose we can operate a solenoid valve uh, based on the output of some sensors, or we can control a relay. We can control an actuator by using some input signals that is given by a sensor. I mean, what is a microcontroller? A microcontroller is a compact integrated circuit which is designed to govern a specific operation in an embedded system, right? A typical microcontroller contains processor, memory, input, output peripherals on a single chip. So that what is an Arduino is it contains it contains a chip which is present here, several input output ports, and with the help of input output ports we can send and receive information and control various devices. So going on to the next slide, just a minute. So these actually the Pir sensors which are present here are not industry ready. I mean, these are basically not used in industries right now. These are only for prototyping projects and like these. So as these sensors are not accurate, we will use a separate microcontroller, that is Node MCU. Node MCU is similar to Arduino, but it has a Wi-Fi chip, that is ESP8266 Wi-Fi chip built into it. So previously we could control the Arduino by using only localized programs written into it. But now, as there is an ESP8266 Wi-Fi chip attached to it, we can control the microcontroller remotely from anywhere around the world, as long as it's connected to the internet, right? So previously, we were controlling the lights of the room by using sensors and stuff. Now there is no headache of placing the sensors. What we'll do is we'll connect the Wi-Fi module to the internet, send signals to the module using our smartphone, and that's all we need. So the flow diagram is here. We'll connect. There is an app in the Play Store called Blink. We can use the Blink library for this. What we'll do is import the Blink library in the script that we write in the microcontroller unit. We connect this node MCU to the Wi-Fi, to the Blink server. The smartphone is also connected to the Blink server, and the smartphone, when we press a button like on or off in the smartphone, it commands the relay, it commands the microcontroller to tell the relay to switch on or off. And hence, we can similarly, this part remains the same. We can switch on or off the LED bulb right now. So we press a button on a smartphone. The smartphone connects to the Blink server, which is connected to the node MCU. The node MCU commands the relay to open its contacts or close its contacts. And similarly, if the relay opens its contacts, the appliance gets switched off. And if the relay closes its contacts, the relay gets switched on. So apart from these, we can attach several sensors to the microcontroller, take input from them and also take output from them. We can do numerous things to it. Another application that I can tell you is that suppose you want to log the temperature of a body for a long duration of time. So what will you do? There are several temperature sensors that are present, that is DHT11, DHT22, LM35, TMP36, infrared sensors, infrared temperature sensors that are present in the market. So we will connect our temperature sensor, take the readings from the input port of it, make a server write a script in to log the temperatures using DBMS queries, and after that microcontroller logs the temperature from the temperature sensor, it sends the data to the database, and we can see all the log data of the temperature there. So this is another application in which the node MCU can be used. There are numerous real-life problems that can be solved using this development boards. Road safety, determining the quality of water. You can use these in the fields of healthcare by using sensors such as the heart rate sensor, the body temperature sensor, several of these. So apart from these, there are many open source development boards that you can see here. Actually, these open source development boards, I personally have not worked in the open source development boards, but I knew these were there, so I presented in the presentation. So you can search these development boards on the internet and can get all the details about it. According to the needs of your project or the prototype that you are building, you can choose the development board that you need. Suppose you are doing a project on machine learning, which needs a bit of computational power. So instead of using an Arduino and establishing a serial connection between your PC and the microcontroller, you can obviously use Raspberry Pi or any other development board listed above, and that can solve your task, I guess. Now, proceeding to the next slide. So many of you have, I think, participated in hackathons, and many have not participated in hackathons. So I want to just say that how to approach the problem statements in hackathons. That is the design thinking approach in hackathons. So what is design thinking? Design thinking is a creatively structured approach that helps an individual or a team to identify the real problem and ultimately solving it. The reason to use this in a hackathon, because it needs to generate ideas fast, but most teams are actually suffering from finding out the true problem before diving into solving it. Design thinking will help the structure. Design thinking will help to structure our thought process and help us identify what problem that is most important to solve. So there are mainly 4 steps through which we can approach a problem statement and build a prototype according to it. These are, at first, we have to choose the problem statement that is given to us according to the technical domain. It may be a software-based, it may be hardware-based. After that, we have to think on the technology that we have to use on the problem statement. We have to make a list out of it. So what are the technologies we are going to use? After that, the most important step that we have to perform is task segregation. If you are with a team, then assign particular task to particular team members. This will make the process easier and faster. After that, the last 2 important steps are prototyping and testing. test repeatedly until and unless you are getting satisfactory results. So these are the main key points that you have to remember when participating in any hackathon or any innovation challenge. So that was all for my part. Hope you enjoyed today's session. You can connect with me in LinkedIn, and if you have any questions, you can mail me here. So that was all from my part.
Devojyoti, can you please address all the questions that are given in the chat box? I guess you addressed most of them.
Yeah, I've addressed most of it. Yeah, like we can use a transistor with a buffer in this scenario. Uh, Sorry, I didn't work with any transistor. Actually I'm a student of electrical engineering and have mostly worked with the microcontrollers that I've listed down. So
No, I was asking about that first scenario when the PIR sensor sends the signal to the microcontroller and which
yeah,
switches the relay in
yeah.
it. So my question was that we can just use a buffer or a transistor which would act as a switch, and then like a microcontroller for that task might be a bit
Yeah, you can
costly.
do so.
Yes.
Yeah, you can do
That
so.
was just
Yeah, you can do so. That will be a low cost solution. And yeah, I think I've addressed all the questions. So I want Somdev to take
Okay,
over from me.
any more questions, guys? Otherwise, we'll be starting off with Avijita. Okay, so I guess that's all. Abhinav, can you please call upon Avijita to present his slides?
Yeah, hello. Yeah, hello everybody. Sorry for my voice. Right now, I got cold. So yeah, good evening everyone. I am Avijit Das. I'm currently working in Infineon Technologies as a senior application engineer, and I pursued BTech, from this college, NSCC, and I'm from the AI department. So I'll go with the presentation. Most of the thing Devajyoti has told already, but here it is. Yeah. Is my presentation visible? Yeah, just a moment. So the art of electronics. This session is about. I want to make sure that I know many of you know that the hardware part, the electronics, which is the hardware part. So like you can create many art with that. So and also honorary to that book called there's a book called The Art of Electronics. So also an honorary to that book, Art of Electronics. Do check it out. Like if you want to know electronics from the core and from basics. So yeah, and by that we I'm starting this session. So as you all know, around 40 to 80% of devices around us are electronics. If you when you are sitting here, so you can see like all the equipments that are around you are most of them are electronics. So why are we so attached to these electronics? There were time when we used to stay without electronics, but now why are we so attached with this electronics? First of all, it's effectiveness. Like one thing which a electronic system can do is not such easier for any another system to achieve that same robustness, I mean same efficiency or all those. So the first step is effectiveness. Like today's systems, electronic systems are much more effective, much more, they are working much effective and faster comparative to the traditional systems, where you use some mechanical devices to control or power or some to, even there are analog, maybe many of you have known that there were mechanical calculators were still there, where calculations were done using mechanical motors. Even if I guess many of you have seen the movie Imitation Game, where Alan Turing was building a encryption device which was totally a mechanical device. So in traditionally, those are mechanical devices, and mechanical devices, they produce sound and they are much more. So in comparative to that effectiveness, electronics is a good player in that field. So that effectiveness, obviously, like since they are much more effective, they are efficient. So industry needs this efficiency. Like if you can go, if you can make a system 1% efficient than your previous system, that's your achievement too. Like you can, that's a big achievement, I mean that's what I mean. uh, so it's much more efficient than the traditional systems. Configurable. So configurable means like nowadays electronics, with electronic devices, they are pretty fast configurable, that you can configure those devices much faster than those traditional devices, like the mechanical ones. I heard Devojyoti was talking about Node MCU and Arduino. Many of you have, I guess, know about that part, that Arduino, that thing. So as a prototype or as a maker, you all guys will be working with Arduino and all. So what is that? It's a configurable IC. Like you can configure that device into to emulate some tasks which are emulate the projects that you were talking about. Someone said smart lights, and many all those. I'm coming to those. I'll be giving that this general gist. Like we are surrounded with electronics and all these things. What are the things? So yeah, hang on with that. The next is the controllable. Of course, why we are using this electronics to control something. Um, you need. Devajyoti gave an example of smart light when he was saying about that you want to turn it off or turn it on when you are not on that place. So you can do that. Like all these are controllable, and this controllable, this feasibility of controllable, that you can control it much, in a easier way, or in a feasible way comparative to the traditional systems. So we are that's why the electronics, these things are here, electronics things are here. The need, the requirement of hardware, it's like is humongous, comparative to this traditional times. Excuse me. Of course it's robust. Like uh, electronics are going to spaces where the temperature is around like minus 40 degree or minus 180 degree. Like those temperature, uh, your electronics has to be that much temperature, they can fight with that temperature and work correctly. They have to be that insulated and all, protected from all those uh, noisy environments or such temperatures. An example is a temperature. There are many other physical parameters too, which as an industrial you have to look after. And as what are the parameters? So like the robustness, it's one of the most important. Like how robust your system is, like how it's immune to the noises which where in the system is placed. um Noises, I mean the electrical noises, that is like there is a general fluctuation of light or fluctuation of voltages. All are voltages, all signals are in voltages. So yeah, like how robust your system is, that point. So with electronics, this robustness is with very high robustness. Electronics hardwares are, there are hardwares coming which are specifically built for this robust purpose, this robust systems. and fast, of course. Like today, your computer on which you were watching this video, it's computing like around, if your computer is processing at 3.9 gigahertz. Many of you have heard about this number, 3.9 gigahertz. So it's like it's computing 3.9 billions of instructions per second. Where are these instructions coming from? These instructions, there are instructions by which your computer can know what you are trying to do with that computer. These are the instructions. So like your processor is like computing 3.9 billions of instructions a second. Unlike that, the traditional systems is where mechanical devices, like they used to turn around, move and move and move, and when the result will come out, they also don't know. So of course, like it's very fast comparative to others. And also, like it's one of my favorite aesthetics, like comparatively to those. Aesthetic means, suppose you are using a wireless remote to control your TV. You don't have to move and go and to change the something. These wireless things, sleek designs and all these. The small, like the electronics industry has grown with the VLSI part. Like the electronic chips has shrunken to so small that you can fit everything inside in your fingertips. So, and all these about like there's those sleek designs are only possible with this electronics, this part and this small. So yeah, like and the aesthetics, it's one of my favorites. So yeah, so this is why we use this electronics, the hardwares in this part. We are surrounding most of the times with the electronics. So next, the electronics in the industrial part, where the electronics is very applied. Of course, the automation. You want to automate, like the Vijay was giving that example of that automation, that part. So automation, you want to automate your home. Many of you have heard about this term, the smart lights, or IoT controlled home automation. This home automation, you want to automate something. You want to make something controlled by your hands, or I mean, you don't have to move here and there to execute that task. So you want to automate something, or you want to make a brain, like you want to make an artificial brain which will do the task for you, automate that task for you. You don't have to go and put the same commands again and again. So the automation, this part. Communication, one of the biggest platform where electronics industry is the communication part. Like many of you heard, or you will this part, like Voyager 1, it's still communicating. Voyager 1 has surpassed our solar system. It went away from the it took photos, and it went away beyond Pluto, and it's still communicating with us with the Voyager 1 satellite. The Pluto, the New Horizon satellite, it took around 9 years to reach Pluto, to just take one photo. So this communication, this part, all these are possible with these this electronics, this electronics part. Before the electronics, it was nowhere with this, and the feasibility of this communication was not so much easier. The computation, like last time I told, the speed our processors are today, they are computing. You want to crack, like there were cryptographers where you use encrypt your data, like this 256 bit of encryption. When you use your WhatsApp, when you open a chat with a new person, you see there, like there is this called 256 bit of encryption of your chats. So what is this 256 bits of encryption? Like you need like 2 to the power of 256 number of combinations to crack that messages, to crack messages, which is very likely to be like it will take millions of years for a for Google's computer, like not one single Google computer, like millions of Google's computer will take millions of years to decrypt that thing, like if they just use hit and trial methods to decrypt that data. So but still, like see, like like nowadays there are GPU, like there are systems, or there are hardwares, application specific hardwares, we call them ASICs, application specific integrated circuits. Those are used for like only for that application to encrypt or decrypt some devices. So like without this computational power, we were we won't be able to encrypt our datas or like do maths. Like even if you take an example, like you can just calculate the you can calculate, you can formulate Laplace values, like you can solve differential equations. How it's coming, like how are all these uh, how they are computing. They don't know how to, like they can't see a maths equation and they can find the results. They will do numerical analysis. They will go one by one, and all these things, this takes time and computation. Like without high computation, this is impossible. So of course, like computation. The automobile sector nowadays, you must be hearing, like many of you have heard about Tesla, I'm sure. So like about Tesla, they are going to create the future of automobile industry. Like they are talking about these electric cars where you can sleep and this car will drive you to your destination. So not only with the cars, like automobile, this can go with like to anywhere heavy machines are there to transport or similar. It can be a train, it can be bus, it can be any. So this automobile sector, like this this electronics has a very high uh, you know future in this automobile sector, automobile part, ATVs. In the medical sectors too, like many of you in the medical part, where uh, if you many of you have heard about electron microscopes, right? So these whoever from the instrumentation background, like they will be studying about these instruments, where you have to do apply your electronics into those instrumentations purposes, where you will be using uh, interfacing with instruments, and the medium will be the electronics. So suppose like is the in this medical purpose, in medical field, on the electronics, like nowadays many humans are trying to create the next human again. So in the medical field, of course, it's a great application. Robotics, who doesn't love robotics? And robotics, like nowadays, yeah, in the previous time, there were robots where they used to use traditional only motors and all those relays systems to control the arms, or not only control the arms, even there were logic with relays, mechanical relays, where to say the robot will go left or right, or just all these purposes. But nowadays, like there were intelligent robots, like many of you have seen the Boston Dynamics. Do follow, like if you didn't watch it yet. So Boston Dynamics, they create great robots. So their robots are very amazing about in the field of like defense, or like household works, robotics, all because of these electronics. And of course computers, electronic computer is an electronic device. The optics, in the optical field, communication, optical field, like today you are these LEDs, like these are 90% efficient than the incandescent bulbs. So these are like the optics, this part, uh, photos, these LEDs, or well, lights, when we are talking about lights or lasers, electronics, like all these are these electronics devices. So yeah, and the application of optics, and of course power electronics. Today you can power any you are able to power devices. uh, One of the most important factor of electronics industry is the power. If you can save like 1 microwatt of power, then also your system will be called bit efficient than the previous one. If you are able to save 1 microwatt, 1 micro means it's 10 to the power of minus 6 times. Even like that small amount of power, if you can save by your device, that also is your achievement, and it will give you a push or a plus to the traditional device which are currently placing in the which is in the market. Say someone built a device which is around which consumes around 10 microwatts of power, or say 20 microwatts of power, and your device just does a bit better, and it consumes like 9 watts of power. So that too is a big achievement for you, and it will give you a very amount a big in the long run it will give you a plus point, and it will push your system. So the power electronics, I just told about the power and the applications, like where you use electronics to power some other devices. We call them power electronics. We have heard about like there is conversion from AC to AC using transformers. Many of you who are familiar with transformers, they must know that we can step down voltages with transformers and step up voltages with transformers. But this was only applicable with the AC circuits, not with the DC ones. Like DC, you can't step down DC voltage with transformers. But in power electronics, with the help of power electronics, you can step up DC voltages. You will push the 5 volts DC inside, and it will give you out like 35 volts or 110 volts. You can control those. So this part, like there is this part of electronics where it deals with the power, and we call them power electronics. Industry is also uh, need toward this power electronics, this part, the electronics industry. So like whenever we will be talking about circuits like electronics, these circuits, so ultimately we will be building circuits. Like the last time when the Vijay was giving that example of you know that that light bulb, the Arduino, all those. So like there remains a circuit where you will design a circuit, and that circuit will work according to you. Like you design that circuit for a purpose, and it will give you that purpose. So what are these types of circuits? What are these types of circuits? So it can be generally categorized into these three: this analog, this digital, and this mixed analog and digital, AD. uh, Analog circuits are like when first electronics were getting into that market, uh, that tube amplifiers, many there were in the early 40s, in 40s, on those times there was this vacuum tubes, where these vacuum tubes are used to control the flow of electrons. Electrons are nothing but electronics is nothing but the study of flow of electrons. So these vacuum tubes, they are used to control the flow of electrons, and with that we used to build amplifiers, radios, and all those. So but analog is still like it's also there, like not it is just an example of the past days. There were analog computers too, like you can compute some value using analog computers, and to be honest, like it's much faster than the digital ones, which can compute the some value. There are analog computers which can compute some result which is much faster than the digital computers which you are using today, or even much faster than the supercomputers. Not joking. Your analog, there were in early days people were they used to thrive with solving differential equations. So the analog computers were there, who used to solve differential equations for you, who used to give you the constant values which you can put inside those. So there were analog computers. uh, there were analog radios, there were analog TVs, like those antenna which we used to set up in the on the roof to for a better signal. So this analog. The digital, like nowadays everything is digital. Like you see which any device you are seeing, like those are controlled with digital devices. It there are like two discrete levels, like the zeros and ones, binaries. We call them bits, binary digits, bits. It's an acronym of bits. So binary digits. So with zeros and ones, with voltage levels 0 volts and 5 volts, we use to this digital part. In the digital part, we make circuits with digital analysis and logic circuits. We can make logic circuits. Even your computer is nothing but a bunch of logic circuits, your computer processor. You can make one processor with those bunch of logic gates, two discrete logic gates. Yeah. And finally, the most robust and most used one is this mixed AD, mixed analog and digital system, which we use nowadays. Like every devices now you are having is consist of this mixed AD part. Like it consists of this analog, which senses the physical environment most of the time, and this digital part which computes and it actuates thereafter. For example, like your microwave oven, if you take your microwave oven, it heats up automatically and switches off at a point. So how does this happening? Like there is this analog sensor, analog temperature sensor, which is reading the temperature and telling the microcontroller, which is a digital device again, to switch it off or switch it on or actuate or something. So mixed AD, it's one of the like nowadays it's used heavily, and the industry in this mixed AD analog and digital designers, there's a very need of these analog and mixed analog and digital designers. So with that being said, like if you want to be these the designers, like if you want to design, where you can start from, like this designing this part. Like there are CADs, computer drafting and drawings, like these CADs softwares. We call them, for electronics, we call them EDAs, electronic design automation softwares, where you can go and put some put some ICs to synthesize your circuit or to predict what your circuit you are trying to build, and you can do that. Here is a example from a spice simulator. So there are spice simulators you can use, like P Spice, LT Spice. Use those spice to design circuits, electronic circuits. How you are going to design electronic circuit? Like say this is an op amp. Like when you start uh, building electronics and the hardware, I'm coming to where is this hardware is very important part when you are going for any any project. Like any project, you should very well aware about that hardware, what that hardware is, when you are trying to implement, specifically in the IoT field or any other robotics, all those. So yeah, so like these are the op amps, like there are few capacitors, like there are resistors. So all these are very plays a vital role. Like each component has its own no own process and own uses, own roles. Like so these how mixing, like if you mix one, start experimenting with these CADs. Like you can uh, build, you can experiment, you can know the behavior of how a op amp can, they can deliver some purpose, or it can go like with your desired purpose. So yeah, use these CADs. Like there are MATLABs, there are VHDL, where you can use digital VHDL is a digital logic synthesis software. Verilog is similar like that. RTL designs registers transfer level, like these logic synthesis, where you can design like ICs about. So do get these softwares. So there are many open source softwares. There are two, like Logisims, like LTSpice. You can use them to make one you can hands on these hardwares, build these hardwares. That being said, like when you are just get a gist about like electronics, this field, I want to talk about this IoT, like this trending topic with this Internet of Things. Excuse me. So this Internet of Things, why we calling it Internet of Things? Internet, the one that connects, of course, like internet connects us. It's and the things, the everything you see around you are things, and these things terms is from that. Like everything around you, your TV, your phone, your washing machine, your geyser, your printers, your mixie, like anything. Anything are like these are all things, these electronic things. These are the real time hardwares, which are supposed to get connected. Like it's similar, like we are connected on the social medias, we are people, we are human, we are connected to each other. So like us, we are also trying to connect these machines, these devices, these things. Every device around you are things. Internet, it's the virtual system, that social part. When you use Facebook, that medium, it's the medium. Internet is the medium, it's virtual, it stays somewhere in the air. uh, Whereas these things, it's physical, it's real, like you can touch it, you can face it, like you can change it, you can configure it in electronic devices. And the internet, it doesn't only has to be this internet. You don't have to go to this world, in the world web. This part, you can make your intranet too, like you can make your intranet with technologies like LoRa, uh, or all those. So you can use that as an intranet to connect your devices. The benefits of IoT, well, why will you use, like why do you want to connect, like there must be this purpose. So suppose you want to run an organization, or you want to you want to make a business, or you want any for your purpose, like there is, if there is purpose. So overall, like this, the processes that you want to monitor, like one of the biggest application is with IoT is monitoring. You go and search with IoT monitoring, and there will be like millions of topics that will be flooding in your feed with the monitoring this part. So yeah, of course, like we use this IoT to monitor, like say you want to monitor the temperature of your pet house or something, or or you want to monitor a temperature of your incubator, or anything. So for that you need to monitor. So you are saying monitor, so there is this sensing this part. With intranet and internet, you can do this. Improve customer experiences, like we will be using a products like these. When you ultimately you are designing some device, you want to sell it. So of course, like the customer over time, they will go hassle free, like they don't have too much hustle to get into some stuffs or into that. Of course, it saves times and money. In the long run, it saves a lot of money, a lot. Enhance employee productivity, like whoever, say if you're monitoring office or something, of course the productivity. Of course, in the last, it can generate more revenue, like since it's saving time and money. They are both they are both, different uh, different entities. Since you are able to save both of them without sparing one or other, so you of course you generate more revenue with that trade off, that part. Applications of IoT, many were talking about, like these business to customer, consumers, like these things. Smart home, smart appliances, elderly care. Smart home, you want to monitor your home. You want to just switch it off, like you are on the fifth floor in an apartment, and you forgot to switch off the pump, which is like on the ground floor. You can just open your phone and switch it off from there. Smart home, you make it smart. This smart word is going to be most used word in this decade. I'm very sure about this. Like you can go, the smart, everywhere you'll be hearing about this smart part. These smart appliances, of course, and elderly care, that part. Industry and farming, of course. Industry needs IoT. Like there is this term also called industrial IoT, industrial Internet of Things, where you use in the IIoT to monitor, automate, and actuate in industry, a whole industry. And there are industries which are fully automated and connected with these Internet of Things. This part. Infrastructure, Bhopal is one of the smart city. They are now get and they got connected with each other's, like the street lights. They are trying to connect street lights where in India, like this. It's going to be a smart city soon. Energy, utilities, environmental monitoring. Environmental, like there are many places where you want to monitor the environment, that part. So yeah, for that infrastructure. And e-commerce, like commerce, on the commerce part, I want to track some, the transportation part. Like each vehicles are connected to each other using this internet, where the vehicles are acting as things to the on this part, this system. So Now how will you proceed with the, like, when how will you proceed with a design? How will you go with this IoT, this part of this design, this thing? So first set your objectives, of course. Like, know what you are trying to build. May it can be just like the scratch it with, hold a pen and use your paper, like just scratch it with block diagrams. Set your objectives, like what I'm trying to do. I'm trying to automate my home. So what I will do, like I will try to turn off the bulbs. Not only bulbs, there can be some microwave ovens or some heating elements, say geysers, where I want to control it uh, when it reaches a certain temperature. Of course, like today there are certain these geysers are there, where all geysers are, most of the time they are automatic, like auto cut. There is this auto cut. But say you have a open loop system, like a heater, where you place the heater in the bucket and you just want to monitor that. So of course, like what is your goal? Set that objective, scratch or is a block diagram. Search in those like out use cases, like how many you have used, like where are the uses, like how good your device will be in the market, or say your as a system, how efficient your device will be. But do get started, like get yourself started with basics and to start. And one of the most important, like of course, whenever these objectives these are set, you have to decide a correct hardware. Like you can use any like there are hardwares which are specifically built for some purposes. You can use those hardwares. Don't use we know for a prototyping purpose you can use generalized like Arduinos, Node MCUs, ESP 12, those devices. But when it comes to like you want to make your device as a marketable or such like that, do search for application specific devices. Like I want to use that device for that application only, and there are hardwares like for those applications only. Do search for that and decide like which correct hardware you will be selecting. Select the IoT tools, like there are these internet of things, these tools, like the virtual tools softwares, like there are on which platform you are trying to go. The platform, yeah, like right now I said like the IoT platform, like there are MQTT, the protocols where you will be implementing this IoT. Like there are MQTT protocols. There can be these direct over server. You can transfer your data directly to a server and you can fetch those from a database. You can do that. MQTT protocol is one of the most nowadays, like they are very lightweight, and it can be used in today's, they are getting used in this industry nowadays. And prototyping and implementing, of course, whether unless you build that hardware and make a prototype, you won't be able to know the results. So do implement that. Gather useful data, of course. Like in the end you need some data, like calibrate your device, to calibrate to know how robust your device is. You need the data, and data will come from your device only. You need to know your device. uh, you need to learn that what your device can do and cannot do. The implementations, like the last time, like in this IoT, everywhere, like automotive, the payments, the cities, energy, security, wearables, logistics. So yeah, IoT is everywhere nowadays. The future of IoT is very high. Like you can go like wherever, thinking of like I want to make some projects with IoT and I want to go pursue that IoT, that part. So yeah, it's a good future ahead, like with this IoT part. But do know that you need to know the intricacies, like how to make it like to more industrial standard. As a maker, you can go first, go get your hands and get started with writing with making some circuits and writing like the logics and all doing. You can go with that first as a maker, then try to make it a more professional by using the application specific. Industry loves this application specific this part, and they are ready to like give you a very high, you know, they want people who knows the applications with this part. So uh, with not being so much general, like if you know a single topic, just go for that topic and you are good to go with that topic only. They just want you to know the industry will put you into that field where you will fit the best. So if you are trying to know a topic, just get to know a topic to its very best and to all the intricacies. So yeah, that's it, like that's from my side. uh, Thank you. Any questions? Highly appreciate it. Like, if you want to questions, any questions?
Yeah,
Okay.
Vijita, it was a really amazing session. It was
Uh,
very engaging and thoughtful.
Thank you. So,
Any questions,
difference
guys?
engine. Yeah. Yeah. So here, Aishwarya Barik has talked about difference engine. Yeah, difference engines by Babbage. Yeah, like the early days. Yeah, correct. The Enigma machine. Yeah, that was the Alan Turing decided to decrypt the. Yeah, correct. So, spot mini. Yeah, the Boston Dynamics. Okay, so then chat about the LiDAR. Yeah, LiDAR. Of course, like nowadays we use LiDARs to measure distances on this part. LiDARs. It's a pretty fast device comparative to the sound and echo, that part. Triodes and vacuum tubes. Yeah, like the analog amplifiers, like there were triodes and vacuum tubes in the olden days. Nowadays still gives when guitar amps. Yeah, it's very true. But when you compare with that sound value with the efficiency in the long run, the electronics are still pretty like with that price. If you go like there are, yeah, they are still on the market, like for aesthetics, like they are still on the market, like they do engage, they do get engaged. So yeah, that can be.
Actually, the thing about those vacuum tubes were that with the temperature and humidity of the day, the tonal quality used to change of
Exactly.
the amplifier.
Exactly. And with more usage, like when you use it like one or two or many times, like a million times, so due to the that work function, that part, so that diodes, all those, the filament, they get weared up, tear down those, and it won't work on a long run comparative to an electronics. But yeah, they are still on the market. Yeah. Yeah, analogs are good at calculus, correct. Why is 5 volt and 3.3 volt so famous? Yeah, good is a good question. Like why it's a 5 volt? This 5 volt logic, mostly like nowadays, like 3.3 volt, this logic is famous. It's similar to that value, like when you are asked with resistors and all those values. So with these combinations, you can go with all the possible logic transitions very smoothly comparative to others. First, like there are very weird values of resistor, like 47, 47, 21, 29, or all these values. Like with these combinations, you can switch levels on the values. With the 5 volts and 3.3, even 12 volts is famous too. 12 volts, 5 volt and 3.3 volts. Like you can switch it with many, with different levels. So yeah, and like when you go inside voltage regulator circuitry, so you can see like this is much more feasible to you know get the voltage as a 3.3 volts compared to 4 volts using those discrete components like discrete capacitor and resistors. So this is why the reason why 3.3 volt and 5 volts is very famous. So yeah, uh, you know any questions? Why is CMOS getting due to high density? like this CMOS. Like when you try to switch components, like in this CMOS, they are also uh, transistors only, MOSFETs, complementary MOSFETs. So metal oxide semiconductor, this transistor, field effective transistors, and TTL is a, so like with comparative to CMOS, CMOS are very dense first. They are very power efficient comparatively to the TTL. Like if you want to switch a transistor like a BJT, bipolar junction transistor, and you need current to pass through, whereas in MOSFETs you don't need current to pass through. So if there is no current, there will be no power loss. So with CMOS, you can just apply. CMOS works on field effect. You just change the field. So there can be like there will be no flow of current too. Like just changing the field, you can switch them on or off. But in TTL you can't do that. TTL, there has to be there has to be a current draw or movement, like there has to be a current to flow in order to switch them. So of course, like the power is much higher in TTL comparative to CMOS. There were many factors too, like on the high density, they can CMOS can turn buffer, whereas a TTL cannot buffer itself. You need external buffers to drive other TTL devices. So yeah, well, old MC1 pick, in the industry, this pick, like with the price range. Suppose you don't want your some pre-processing task, and you don't want your Wi-Fi device to get involved on that pre-processing task. So in the industry where your computer has a co-processor too, so for that co-processor part you can use these low power microcontrollers. Of course, a microcontroller containing a Wi-Fi will consume high power, and all everything is boiled down to that power factor. So of course these small big and old AVRs, they are still manufactured, and they will still get manufactured in the upcoming days too. And the VLSI workflow, yeah, like for the VLSI part, start yourself with, first I will ask you to start yourself with logic designs, like the logic gates. First, get yourself familiarized with logic gates, how you can derive a function with the logic gates. Next, you can go with the logic gates to build. Um, as a transistor, you can build logic gates using transistor. So try to build, say if you want to build a circuit using logic gates, first you do that in a CAD. uh, Next, you try to build those logic gates with transistors. You build with a circuit is built using just transistor. Now you boil down those transistors into that chip level, those in a VHDL, or on those very an RTL design, that part. Softwares, I won't be directly biasing any software, but there are many softwares out there. They're pretty costly, but you can get open source too. Um, do use those softwares to get, but I'll ask you as a beginner, first go and start with logic designings and synthesis, that part with transistors. So yeah. Yeah, thank you. Any more questions? Okay, I guess we can wrap up now. It's already 9:15, and yeah,
Yeah, thank you, Abhijit, for the wonderful session. So with this, we can end today's session with Debajyoti Da and Abhijit Da. And I just wanted to add one more point to those present in this meeting. We have been live on YouTube all this time, so you can watch this session again on YouTube if you want. And this is on GNX official YouTube page. So yeah, we can wrap up this session today.
You can share the
Link,
YouTube
okay, I'll just share
page.
the link.
So, guys, I think that's it. You may leave now. We had a lovely session today.